We want to talk about the behavior of functions on a metric space X by looking at its behavior on restriction to curves in that space. So we need to talk about precisely what we mean by curves in a metric space. To begin with, we will always only look at continuous curves. So let's say it's a continuous function from a compact subinterval of R1 into our space. We should distinguish a curve from its image, which is a subset of X, and which can look nothing like a curve, given the examples of space-filling curves, or how often it can self-intersect or overlap. Also, if you look at a circle as a subset of R2, as a curve, you don't know if it has traversed it once or twice, in the positive direction or in the negative. So that's why the definition, the more useful and workable definition is that of a function from a compact interval. So to rule out the scary examples of space-filling curves and whatnot, people have come up with what is called the notion of rectifiable curves. So we will say such a curve is rectifiable or of finite length if, similar to definition of BV functions, you partition your interval AB into finitely many subintervals. You choose increasing sequence of points. And then you look at gamma ti and gamma ti plus 1. So these are 2 points in your space, and it's a metric space, so you can put distance here. It's truly here that we use metric because continuity would be defined even for topological targets. And then you sum this over I. So let's say from 0 to n minus 1. And then you look at the supremum of all such creatures. And you say if this is finite, then you say the curve is rectifiable, and you set this quantity to be the length of gamma. So we should finish by saying what this supremum is taken over. So where supremum is over all finite collections of points where t0 is a, t1, t2, finitely many until you reach t n minus 1, and then tn, which is equal to b. So if over all such partitions this supremum is still finite, we say the curve is rectifiable or of finite length. This immediately rules out many crazy examples like the space-filling curves. But still, it can visually be quite complicated. The most important theorem regarding this notion of rectifiable curve is the following, that if gamma is rectifiable, then there exists a curve, a second curve, alpha, from a different interval, and that interval happens to be of length equal to this length. So length of gamma, which is a finite value because gamma is rectifiable, and you put that number here and you have this interval, so you have a new curve into X. That is much nicer curve, such that part A is that for every point S that you pick in this 0 and L gamma interval, it is true that the length of part of alpha from 0 to S, these are, of course, you've seen all of this. Restriction is obviously defined the same way, and you know that if the full curve is rectifiable, definitely a part of it is rectifiable. So I leave all these very easy details to you. And this length happens to be exactly equal to S, which explains why the only number that would fit here will be this. We see that, let me put an I prime here. In particular, we see that alpha is 1 Lipschitz. It's an isometry indeed, because the easiest proof is that, well, alpha of S, the distance of alpha S from alpha S prime for any choice of S and S prime in that range. So this is less than or equal to the length of part of gamma restricted to S to S prime. Let's say S prime is the bigger one. This is always true. The end points, because in the partition, in the definition, if you take just two values, you take just T0 and Tn, then this supremum is just distance of the endpoints. So the distance of endpoints is always less than the length. That's very easy observation, but something one forgets to utilize effectively. But anyway, so distance of endpoints of this curve, which is here, is less than the length of that curve, and we said that this is nothing other than, from this property, we can work it out to be S minus S prime. And this is for arbitrary S and S prime, which is exactly showing that the curve is 1 Lipschitz, so this inequality with factor 1 is true. Okay, but so far my theorem is just a silly claim that if you have a rectifiable curve, there's another curve with these very nice properties. But what is the punchline? So what does that have to do? What does that say about our original curve? And number two, our original curve comes from this other curve as follows. So what is called an increasing change of parameters. So gamma at every point S is alpha at h of S for some increasing function h from, so yeah, so gamma's domain of definition is AB, and alpha's definition is from 0 to length of gamma, right? So this is saying that if you just play with the time variable, so in the definition of a curve, you can think about this inside variable as the time variable. And this is saying that if you correct how time flows with this function h, you can turn gamma into another curve alpha, where alpha now has extremely nice properties. It's an isometric embedding of the interval into the metric space. This is so important. This is saying that all rectifiable curves are, from metric viewpoint, just the same. They are segments. This is, you have to compare it to two-dimensional theory with two manifolds. Not all two manifolds are copies of R2, pieces of R2, because of this curvature issue. But this says that in dimension 1, there is no truly different one-dimensional object than R1. All rectifiable curves are isometric copies of some segment of R1, of course, that segment. The only restriction is being how long that segment is. Okay, so this is quite easy to prove, but also it's not trivial when you think about it. An exercise that I've seen in notes of Piotr Hajwasz is the following. So take ft from 0, 1 to 0, 1 be the counter Vitali function, which we saw in previous lectures. It's not absolutely continuous. Fundamental theorem of calculus fails. It's differentiable almost everywhere, but the derivative is 0 everywhere that it exists. And let this curve gamma of t be t and f of t. I can just work with f. F is actually an example of a curve, the target space x being R1. But to kind of make it visually better for drawings, I make it so this becomes a curve from 0, 1 into R2, which is now my metric space x. So the image of that is a curve which travels along this Cantor Vitali set. It travels the graph of this, okay? So whereas if I took f, f would be like just traveling along this line. Now this curve starts at 0, 0 and then ends at 1, 1. So gamma of 1 is 1, 1 and gamma of 0 is the origin. And this one is a rectifiable curve simply by writing that supremum notation. When you take any partition, you can see that the length will be, well, if you take distance of any 2 points here, it's less than or equal to the horizontal distance plus the vertical distance, like you take the L1 norm. And then from being monotone, you easily conclude that this is rectifiable. This is the same as proving why the counter Vitali function is BV, simply because it's increasing. Okay, so, but this one is so gamma is rectifiable. But it is not Lipschitz. It's not even absolutely continuous, so it is not Lipschitz curve. What happens with this curve is that, so if you take gamma from 0 to 1, all the increases, all the length that it accumulates happens along the counter set. So there is this set of measure 0 being the counter set where all the length that this gamma accumulates happens on this. And for anything along here, all the vertical length, I should say, the vertical component. And for all of this part, it only captures the horizontal part. So somehow the length is accumulated out of nowhere. And this theorem, this reparameterization theorem, says that if you pick the right h, which is the exercise, like so exercise is find the right h, or compute it. So the theorem guarantees that there is some way of doing it so that this curve, the new curve, if this is one value to this other value, the length accumulated between them is exactly the difference in the input parameters. So I will not cover all the details of the curves in metric space theory because I have a separate playlist with all of them in it. We've done that before. There are PowerPoint presentations. There are in total 10 videos going in very fine detail into all of these issues and examples. There I also talk, let me show you which videos I'm talking about. So this is the playlist Curves Arc Length Parameterization. So the name of playlist is Curves in Euclidean and Metric Spaces. And here are the videos. There I also talk about absolutely continuous curves, which is a generalization of the absolute continuous functions. it has some relevance, but to not confuse it with absolute continuous functions that we will focus on, I don't want to bring that picture in. I don't want to have two notions of absolute continuity, one for functions, real valued functions, and one for curves. To us, curves will often be parameterized to be Lipschitz, or reparameterized to become Lipschitz. So without loss of generality, under this theorem, we will often assume that a rectifiable curve is already parameterized in a Lipschitz way, or even better, parameterized with arc length. So this alpha reparameterized curve, so alpha is called the arc length parameterization, because you define the arc length and then use that, you kind of find a pseudo inverse to that, which then gives you the function h. And this property is where, then again, it's parameterized by arc length, because you can calculate the arc length simply by looking at the parameter. Okay. In those videos, I talk about also proof of this arc length parameterization. So this counter-Vitali function and curve, corresponding curve, is a good example to keep in mind. A priori, it is rectifiable but not parameterized correctly. The theorem says that you can always correct that through parameterization. Okay. I'm thinking about whether we should continue or this will be enough as an introduction just to rectifiable curves. I think we can do that. Let's keep the video simpler to watch in one go, and we'll continue with the rest of study of rectifiable curves. And after that, there will come the notion of upper gradients in metric spaces.